The battery that was supposed to lose is now winning, and the people who saw it coming were laughed at. For most of the last decade, the electric vehicle industry operated on a simple belief: the battery with the highest energy density would win. More kilowatt hours per kilogram meant more range, and more range meant more customers. The logic seemed airtight. Engineers at every major automaker had run the numbers, consultants had written the reports, and investors had placed their bets. The winner was already chosen, and it was the nickel-based battery. Sophisticated, powerful, and expensive. The other option, a simpler chemistry using iron and phosphate, was considered a budget compromise. A consolation prize for manufacturers who could not afford the real thing. That was the consensus. And then, quietly, and then all at once, the consensus turned out to be wrong. This is the story of how one of the most confident predictions in modern industrial history failed. Not because the engineers were incompetent, but because they were solving the wrong problem. They optimized for the laboratory when the market was optimizing for the parking lot. To understand why the prediction failed, you need to understand what everyone believed in 2021. Nickel manganese cobalt batteries, known as NMC, and nickel cobalt aluminum batteries, known as NCA, dominated the electric vehicle market. They held roughly 75% of cathode demand globally. The reason was straightforward. These batteries could store between 200 and 280 watt hours per kilogram. That is a number that translates directly into driving range. And driving range was the single greatest anxiety for anyone considering buying an electric vehicle. Range anxiety was real. Surveys confirmed it. Dealership conversations confirmed it. The industry had built its entire strategy around solving that problem, and nickel-based batteries were the answer. The alternative, lithium iron phosphate, or LFP, could only store between 150 and 180 watt hours per kilogram. That is roughly 30 to 40% less energy in the same weight. On paper, that is a serious disadvantage. LFP also had weaker high-power performance characteristics, which made it seem unsuitable for anything beyond the most basic transportation needs. The industry view was settled. LFP was a budget option for budget markets. It would never compete where it mattered. Every major automaker had internalized this hierarchy. The premium brands were building their futures around NMC. The supply chains were being structured around nickel and cobalt. Mining companies were expanding operations. The assumption was that energy density was the primary variable the market cared about, and therefore it was the primary variable the industry should optimize for. What nobody asked loudly enough was whether that assumption would hold. Then something unexpected happened. In 2020, the first Chinese manufactured Tesla Model 3 arrived with an LFP battery pack. This was not celebrated, it was questioned. Why would a premium brand use an inferior chemistry? The answer Tesla gave, cost reduction, supply chain resilience, improved drivetrain efficiency, sounded reasonable but also sounded like rationalization. Surely a company with Tesla's engineering resources would not choose a lesser battery unless it had to. The skepticism was immediate and understandable. What the skeptics missed was that Tesla was not making a compromise. It was reading a signal. By 2021, Tesla officially announced the switch to LFP chemistry for all standard range models globally. The reaction was mixed. Some analysts praised the supply chain thinking. Others pointed to the range reduction and called it a step backward. Industry observers noted that cobalt and nickel prices had become volatile and questioned whether the move was driven by necessity rather than strategy. What everyone agreed on was that the decision was significant. A company synonymous with battery technology had chosen the simpler, cheaper, lower density option. The debate about whether that was smart or desperate would continue for years. Here is where the story gets interesting. While the industry was debating Tesla's decision, the data was already moving. LFP adoption was accelerating not just in Tesla's lineup, but across the entire Chinese market, which at that point represented the largest electric vehicle market on Earth. BYD, which had committed exclusively to LFP from the beginning and had been largely dismissed by Western analysts as a low-cost regional player, was scaling at a speed nobody had anticipated. CATL, the world's largest battery manufacturer, was expanding LFP production aggressively alongside its NMC lines. The market was sending a signal, and the signal was getting louder. By 2023 and 2024, LFP had reached approximately 32% of global market share. That number alone would have seemed impossible 5 years earlier, but the pace of change was what was truly remarkable. In China specifically, where the data was most detailed and most extreme, LFP was not just growing, it was dominating. And then came 2025, which is the year the prediction officially collapsed. In 2025, LFP crossed 50% of global electric vehicle battery deployments for the first time. In China, the number was even more striking. 81.2% of domestic battery demand was LFP. The chemistry that had been written off as a budget option now controlled 4 out of every 5 batteries installed in the world's largest electric vehicle market. NMC, the technology that was supposed to win, held just 18.7%. And while LFP grew by 52.9% in China between 2024 and 2025, NMC grew by 3.7%. Not a decline, but effectively stagnation next to an explosion. So what happened? How did the inferior battery beat the superior one? The answer is that it was never actually inferior. It was inferior on one specific metric that the industry had decided was the only metric that mattered. When the market started making its own decisions, it turned out to care about different things. The first thing the market cared about was cost. This is where the numbers become genuinely difficult to ignore. In 2025, LFP cells cost approximately $45 per kilowatt hour. NMC cells cost approximately $76 per kilowatt hour. That is a 41% price difference at the cell level. At the pack level, LFP came in at roughly $81 per kilowatt hour compared to $128 for NMC, a 37% gap. For a 50 kilowatt hour battery pack, which is a typical size for a standard range electric vehicle, the difference was between $1,200 and $1,300 per vehicle. That is not a rounding error. That is the difference between a vehicle that is profitable and one that is not. For manufacturers trying to bring electric vehicles into the price range of mainstream buyers, that gap was, as one industry report put it, impossible to ignore. The cost advantage did not emerge from a temporary dip in lithium prices or a short-term manufacturing advantage. It is structural. LFP batteries use iron and phosphate, which are among the most abundant and cheapest materials on Earth. NMC batteries require nickel and cobalt, which are not only more expensive but concentrated in a small number of geographic locations, making supply chains vulnerable to disruption, political risk, and price volatility. Between 2020 and 2023, nickel and cobalt prices swung dramatically, adding uncertainty to every NMC production forecast. The LFP supply chain had no such exposure. Iron and phosphate were simply not going to become geopolitical weapons. That stability was worth something, and manufacturers started pricing it accordingly. The second thing the market cared about was longevity, and this is the data point that genuinely surprised people who had been dismissing LFP on energy density grounds. LFP batteries achieve between 3,000 and 5,000 charge cycles over their operational life. NMC batteries achieve between 1,500 and 2,500 cycles. That means an LFP battery can last 2 to 3 times as long as an NMC battery before significant capacity degradation. Real-world data collected from Tesla vehicles confirmed this. LFP packs were holding their capacity better over time than nickel-based packs. For a vehicle owner who charges every night, cycle life is not an abstract specification. It determines whether the battery still works at 200,000 miles and whether the vehicle has any resale value when they decide to sell it. The industry had been so focused on energy density that it had underweighted the total value calculation that real buyers actually make. Here's the question worth sitting with for a moment. If you are buying a car you plan to keep for 10 years, which matters more to you, an extra 30 miles of range you rarely need, or a battery that will still hold 90% of its original capacity a decade from now? The industry assumed the answer was range. The market, when given a choice, increasingly said longevity and price. The third structural factor was drivetrain efficiency. This one is less dramatic but quietly important. Between 2018 and 2025, electric vehicle motors, thermal management systems, and software efficiency improved substantially. Vehicles that might have needed a large, dense battery pack in 2018 to achieve acceptable range could achieve the same range in 2024 with a smaller, lighter LFP pack. The energy density disadvantage shrank in practical terms even though it remained constant on paper. The gap between what LFP could deliver and what mainstream buyers needed closed faster than most analysts had modeled. The engineers who built the original forecasts were not wrong about the chemistry. NMC does store more energy per kilogram. NMC does have better high power characteristics. Those facts have not changed. What changed was the context in which those facts mattered. The engineers had modeled the technology correctly, but weighted the variables incorrectly. They treated energy density as the primary competitive axis when cost, cost, supply chain resilience, and longevity were the variables that would determine mass market adoption. It is a mistake that has a name in decision theory, optimizing for the measurable at the expense of the important. Now look at who is winning. Tesla, the first major Western manufacturer to make the switch publicly, has seen the market validate its decision repeatedly. The standard range versions of the Model 3 and Model Y, which run on LFP chemistry, are among the most cost-competitive electric vehicles in their segments. BYD, which committed to LFP before it was fashionable, produced 165.77 gigawatt hours of LFP battery capacity and holds 16.4% of the Chinese market. And CATL, the company that mastered both chemistries simultaneously, reported a net profit of 50.7 billion yuan in 2024, a 15% increase year over year, while holding 43.4% of the Chinese market. The companies that read the economics correctly made money. The companies that held onto the energy density thesis the longest are now scrambling to catch up. The ripple effects extend beyond electric vehicles. Grid-scale battery storage, the industry that stores solar and wind energy for use when the sun is not shining and the wind is not blowing, has adopted LFP almost exclusively. Battery energy storage system pack prices collapsed to approximately $70 per kilowatt hour in 2025, a 45% drop driven almost entirely by the scaling of standardized LFP production. The same chemistry that was dismissed as a budget option for short-range vehicles is now the foundation of the global energy transition storage infrastructure. There is also a next chapter forming. Sodium-ion batteries are beginning to attract serious investment and production commitments, with CATL dramatically increasing its sodium-ion production plans in 2026. The projection from Bloomberg NEF suggests sodium-ion demand could exceed 40 gigawatt hours worldwide by 2030, with some analysts forecasting a 3 to 15% market share by 2035. The GetFocus base case for 2030 shows a segmented competition where NMC stays in premium applications, LFP and its next generation variant LMFP hold the mainstream, and sodium ion becomes a credible third option for low cost, cold weather, and fleet applications. CATL itself has suggested that sodium ion batteries could eventually replace up to 50% of its own LFP volume. That is the world's largest battery manufacturer saying publicly that it expects its dominant product to face serious competition from below within a decade, which raises a question worth leaving in the comments. Do you think sodium ion will do to LFP what LFP did to NMC? Or is this a different situation where the chemistry gap is too large and the LFP cost advantage is too entrenched to repeat the same disruption cycle? The deeper lesson here is not about chemistry. It is about how industries form consensus and why that consensus tends to anchor on the most visible and measurable variable rather than the most economically consequential one. The battery industry spent a decade building infrastructure, supply chains, and investment theses around energy density because energy density was easy to measure, easy to compare, and easy to sell in a product brochure. Cost, longevity, and supply chain resilience were harder to quantify in a headline specification, so they were treated as secondary considerations. The market, operating without the industry's assumptions, weighted them differently. That is what disruption actually looks like from the inside. Not a dramatic announcement, not a single breakthrough, just a slow accumulation of market choices that eventually makes the old consensus look like a mistake that was obvious in retrospect. And the uncomfortable question for anyone watching this industry is whether it is happening again right now. If you are an engineer or investor or executive whose thesis is built on the next generation of high-density solid-state batteries displacing LFP, you might want to revisit whether the market will value what you are optimizing for. The history of the last 5 years suggests that the market has a different vote than the laboratory. It does not always choose the most advanced option. It chooses the option that solves the most problems for the most people at a price they can actually pay. If you want to stay ahead of the next time the industry gets this kind of call wrong, and it will get it wrong again, subscribe to this channel. What we do here is follow the money, the manufacturing data, and the supply chain decisions that tell you where the industry is actually going, not where it says it is going, and that more often than not is not the same place.